So we will, as I said yesterday, that we will do all the revisions once, the exercises and sample practicals once. Yeah. So I hope you have this one. So I'm going to take you through the theory, then we do the practicals on hypothesis testing. So to introduce hypothesis testing, basically hypothesis testing is built on what called a scientific method. And perhaps it is good for us to define what's a scientific method before we proceed further to hypothesis, to define what a hypothesis is and so on. So we are saying that when we are talking about scientific method, we are saying that it is a procedure that has characterized natural science since the 17th century. And scientific methods mostly consist systematic observations, measurements, experiment and formulation, testing and modification of hypotheses. So what is clear is that as time goes by, there is always improvements, right, that happen. So we are saying that since then, we have evolved to the point where most people, and especially professionals, realize that pure observation can be deceiving. Like what they mean, like if you want to make a decision by just observing, sometimes it can be deceptive, right? That's what that statement means. So we are saying, therefore, business decisions are increasingly being driven by data. That's also the purpose of data science. Basically, what that statement means is that in the past, businesses could just make assumptions. For instance, that if it is marketing department, the main reason uh, perhaps why this marketing method is better than this is because of A, B, C, D, and so on, right? Like the perhaps the main reason why social media marketing performs better than the outdoor marketing, like the billboards and so on, maybe because of accessibility to phones and the internet penetration. That's just an assumption. But nowadays, businesses are not just making those assumptions. They want to justify it by taking data and do the test so that they can conclude based on data, not just as an assumption. So we are saying that there are several steps you will follow to reach a data-driven decision. The first one, steps in data-driven decision making. The first one, you need to formulate a hypothesis. Like we are saying that Facebook marketing is better than billboards. Then you want to test to know if it is something that is true or not. Then after that, you are going to find the right test. Am I going to use the Z or the T statistic? We are going to see it later. Then after that, you execute the test. Like you are going to compare the value that you have calculated with the standard values of measurements. These are the standard, like if this falls below here, this is the decision that you are going to make. If it goes above, this is the decision that you are going to make. Then after that, now the last one is decision making and so on. But let us define what is this hypothesis. So when we are talking about a hypothesis here, we are saying that a hypothesis is an idea that can be tested. So we are saying that it is a supposition or proposed explanation made on the basis of limited evidence as a starting point for further investigation. It is just something that you say, but it can be, you can go further, do more research and justify if it is true or not. That's what a hypothesis is. So in hypothesis, we have two types of hypothesis. We have the null and the alternative hypothesis. So the null hypothesis is the hypothesis to be tested. And we are saying that it is the status quo, like what you know. So you need to test to try to prove if it is true or not. So we are saying that everything which was believed until now that we are contesting with our test, that's the null hypothesis. We are saying the concept of the null hypothesis is similar to innocent until proven guilty. And we assume innocence until we have enough evidence to prove that a suspect is guilty. So that's the concept of the null hypothesis. It is something that you need to test. And we have compared it to the aspect of, like in Kenya, you are innocent until proven guilty. Even if you are arrested, you are assumed to be innocent until proven guilty. And for you to be proven guilty, there must be sufficient evidence beyond reasonable doubt that truly you have committed this crime, and so on. So the null hypothesis sometimes we notice as H naught. The H naught, the zero. This one is called H naught, this one. And the alternative hypothesis is denoted as H1 or HA to stand for alternative. So we are saying that the alternative hypothesis is the change or innovation that is contesting the status quo. Like now you are trying to disapprove, you are coming with an idea to disapprove the status quo. That becomes the null hypothesis. So we are saying that usually the alternative is our own opinion. The idea is the following, like basically you have what has been there. You come with your own opinion and say, no, this is how I think about this problem. I want to innovate. Perhaps people say mobile money payment is like if people prefer making payments via mobile money as compared to credit and debit cards and so on. So like you say, the status quo in Kenya currently, people prefer mobile money. Then you want to innovate something to prove if it is true or not. So we are saying that if the null is the status quo is what is generally believed, right? Then the act of performing a test shows we have doubts about the truthfulness of the null. So more often than not, the researcher's opinion is contained in the alternative hypothesis, because when you are doing research, you are trying to prove what has been there. Like for instance, in academia, when you write your thesis or a project, you have recommendations that you put sometimes for further research, so that someone else can pick from there and collect data and try to prove. That is what normally happens. So in research, normally you are trying to disapprove the null hypothesis. If you disapprove it, then now you accept your alternative hypothesis. It means your research, you have achieved the objective of your research. So in research, mostly what the researcher comes up with is what called the alternative hypothesis. So we have what called examples of hypothesis. So as per the logic that we learned in the confidence interval lesson about the salary of a data scientist, the null hypothesis should have been, for instance, data scientists do not make an average of 113 US dollars. So there was another example whereby you could have said the average salary should be less than or equal to 125 and so on. So basically, I want to clarify this statement so that you connect the dots that we carried from the confidence interval. So we are saying in statistics, the null hypothesis is the statement we are trying to reject because it is the status quo that you are trying to reject. Let me check if there's a question. Okay, Jacqueline can't hear me. What about the rest of the team? Like, is it because of the background noise or I'm not audible? Can I see the reactions from the rest? Neymar can hear me. Lucia, can you hear me? Terry? Clearly, am I audible or we have? Okay. Perhaps Jacqueline, you can try and leave the call, then rejoin again. Okay, thank you. You can try to leave, then rejoin again, Jacqueline. Okay. So the first example, for instance, for the data scientist salary example, the null hypothesis will be the mean data scientist salary, which is 113 US dollars. Then we will try to reject the null with a statistical test. So usually your personal opinion, e.g., or example, that data scientists do not earn exactly that much. So that becomes your alternative hypothesis. Like whatever was there is that from here, the mean data scientist salary we calculated, we got 113 US dollars, if you recall very well, on the data set we used yesterday. So, but you are trying to say that data scientists don't earn exactly that much. So that becomes your alternative hypothesis. Like you are trying to disapprove, like you don't agree with this statement. Then you say that no, data scientists not earn such much. In the next example, then you are being told that the mean salary of data scientists is more than or equal to 125 US dollars. So you are saying that, so the alternative hypothesis there becomes now, like you are trying to disagree with this. If the mean salary is more than or is equal to or more than 125, and you are trying to reject that, it means now it will become lower than 125. Because greater than equal to, it means it is 125 and above. So if you are trying to reject, you are trying to, it is the lower value of it. But the first one, we are saying that the average salary of a data scientist is 113 US dollars. But you are saying that that data scientists do not earn exactly that much. So it means that you are saying that because you are not sure that it is more than or less than, the alternative becomes data scientist salary is not equal to 113. It's not lower, it's not like you are not sure if it is greater or lower. So it means it is not equal to, which can fall in between either a higher point or lower point. We are going to see, how to state it. So we are saying that decision you can take. When testing, there are two decisions that can be made. Either you accept the null hypothesis or to reject the null hypothesis. Yes? Okay. Yeah. 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 On the 113, let me see. Which one? This one. In the first or second? The first. But the, oh yeah. So the other do not make should now be this one. Do not make. This one is the null. So the alternative will be equal. That's what you are trying to say. Because you are saying the null hypothesis should have been the data scientists do not make an average of 113. Then, yeah.
That example.
Or I should have. Oh yeah, yeah. I get it. Yeah, yeah. I think I'll correct it. I'll correct it. Yeah. I get it. I think there's somewhere, I don't know if I did input well. Let me check. Yeah, I think I'll check into that. Thank you for that. So this one should come the other side. Like what we are meaning that we are saying that, like we are saying that the mean average salary of a data scientist is 113. So the alternative now becomes it is not equal to. Like, so sorry for that. I'll check and correct, and I will upload this one again. Okay. Perhaps we can move here. Thank you for the observation. On the decision, we are saying that when testing, there are two decisions that can be made, right? You accept the null hypothesis or you reject the null hypothesis. In the concept of innocence till proven guilty, when you accept the null hypothesis, what does it mean? It means that you remain innocent, right? When you reject, it means now you are guilty. Yeah. So to accept the null means that there's not enough data to support the change or the innovation brought by the alternative. And when you reject the null, it means that there's enough statistical evidence that the status quo is not representative of the truth. So it means now you have enough evidence. So there's a diagram here. It has the two-sided rejection regions are here, and the acceptance regions is here. But now we do have what called the two-tailed test and the one-tailed. I think it should be somewhere. The two-tailed test is sometimes called two-tailed. Two-tailed, they are called one-sided. So one tail is one-sided, two-tailed, two-sided test, and so on. So we are saying that given a two-tailed test, in most cases we are going to see when you have equal to, not equal to, it is a two-tailed. But if you have anything like greater than, less than, equal to, those are one-tailed test. So that is what is going to distinguish the two. So we are saying that graphical, the tails of the distribution show when we reject the null hypothesis is the rejection region. And in most cases, we reject the null hypothesis when the p-value, like our alpha, if our alpha is 5%, the 0.05, and we calculate our value, if it goes above 5%, we fail to reject the null. If it goes below 5%, we reject the null hypothesis. Okay, you'll get it as we proceed. So in most cases, we have here the alpha, we have here the alpha. So this inside here is the acceptance region. So it means that if your alpha is 5 here and 5 here, so your values should be in between here, below the alpha for you to accept. If they go outside the alphas here, it means you are going to reject. That's why they are saying the rejection region here. So we are saying that the rationale is if the observed statistics is too far from 0 depending on the significance level, because we say that we have how many significant levels? 3. The 99, 95, and 90. So they are saying that if the observed statistic is too far away from 0 depending on the significant level, we reject the null hypothesis, otherwise we accept. So we have just an example of how we report. If you are going to accept, you can say at X% significant, we accept the null hypothesis, or at X% significant, A is not significantly different from B. At X% significance, there is not enough statistical evidence that this is better than this, something like that. At X% significance, we cannot reject the null. Like, basically, this one is how you should report. Like, they are giving you an example. So on rejection, you can say at X% significant, reject the null hypothesis. At X% significance, A is significantly different from B, and so on. So that's just how you report. But let us look at the level of significance and the types of tests. We say that our level of significance is the same as alpha, right? And alphas are 3 main ones. The 10%, 1%, and 5. So we are saying that the probability of rejecting a null hypothesis that is true is the probability of making this error. This is the level of significance. Is the probability of rejecting a null hypothesis that is true. It's called the level of significance. So we have the common significant levels. These ones already we know, 0.1, 0.05, and 0.01. So the most important is here. The two-sided test and the one-sided test. So the two-sided, also known as the two-tailed test, is used when the null contains an equality equal to sign or an inequality sign which is not equal to. When you have equal to and not equal to, just know that it is a two-sided test. Then, and in two-sided test, you see our alphas we divide by 2. So we have the rejection regions here, the rejection region here. Here is the acceptance region. On the one-sided, or what called the one-tailed test, is used when the null does not contain equality or inequality. So if you find cases you have the less than sign, the greater than sign, the less than equal to, or the greater than equal to sign, know that it is the one-sided test. And there, your alpha you want to divide by 2. So these symbols will guide you to know if it is a one-sided test or a two-sided test. So that takes us to something else which we learn more in machine learning and very crucial when evaluating machine learning models. It's called the statistical errors. We have what's called the type 1 error and type 2 error. So we are saying that in general, there are two types of errors we can make while testing. One, we have the type 1 error, which is called the false positive, and the type 2 error, which is called the false negative. So we have an example here, the truth and the status quo. When the null hypothesis is true, so we have type 1 error and type 2 error. I want you to understand how they come. So type 1 error comes whereby you reject the null hypothesis when it is true. Are we together? Like type 1 error, which is also called false positive, is when you reject the null hypothesis when it is true. It is here. And type 2 error comes when you accept the null hypothesis when it is false. It is also called the false negative. So this one is related to something you will learn in machine learning called confusion matrix. 1001, something like that. You will find this concept. So we are saying that the probability of committing type 1 error, which is false positive, is equal to the significance level, which is alpha. And committing type 1 error is rejecting the null hypothesis when it is true. And the probability of committing type 2 error, false negative, is equal to beta. And this one is a false negative, and so on. That one takes us to the next level, the p-value. This is the most important part also. We are saying that the p-value is the smallest level of significance at which we can still reject the null hypothesis. So given the observed sample statistic, we are going to see how are we going to calculate the observed sample statistics. So notable p-values are 0.00 and 0.05. So when we are testing a hypothesis, we always strive for those 3 zeros after the dot. These ones. This indicates that we reject the null at all significant levels. Like if you test and you get 0.00, the 3 zeros, it means that your alternative hypothesis is true. Like it works, like what your innovation works, whatever you are trying to come up with works. Then we have what called the 0.05 is often the cutoff line. If our p-value is higher than 0.05, we would normally accept the null hypothesis, right? It means that your study is not significant. Because if you accept the null hypothesis, it means whatever you are trying to come up with has failed. Because you are trying to disapprove it, right? So, So we are saying that 0.05 is often the cutoff line. If our p-value is higher than 0.05, we will normally accept the null hypothesis, equivalent to testing at 5% significance level. And if the p-value is lower than 0.05, we will reject the null hypothesis. So in most cases, this part is very important to assist you in making the decision. You look at, is your p-value less than 5% or more, then you accept or you reject the null hypothesis. So we are saying where and how are p-values used. So we are saying that most statistical softwares calculate p-values for each test. Another one is that the researcher can decide the significant level that you want to use. And we said for medicine, it is better you go for, yes, 1%, which is 99% confidence level. No, we were just testing. Yeah, just for practice. But when you are doing the medicine research, you go for the 99. Yeah. We were just playing around with various, just for the purpose of practicing. Yeah.
Who sets the level of significance?
Yes.
Who sets the level of significance? How do you decide
Yeah.
what your level of significance is?
It depends with the research that you are doing. So basically, we have what called the standard. We saw that we had only 3 standard. So for medicine and related, you see, like for medical related researches and so on, they are guided like by the World Health Organization and so on. So they recommend they use the 99% because it is very sensitive, the kind of research. But in most cases, it's any other marketing and so on, you use 95%. Yeah. So those 90 is very rare to use 90%. It's normal 95 and 99%. That's why even when we were looking at the regression, when we were looking at the R squared, if I'm not wrong, we say that if you get 0.95% and above, it means that your model performs better, a bit better, yeah. So another thing is that the p-values are usually found with 3 digits after the dot, like 0.00 something. The closer to 0.00 the p-value, the better. So if you want to calculate the p-value manually, of course we have softwares that calculate. If you want to calculate manually, you can. There's an online calculator here. If you click this, it will take you to a certain page. But in most cases, a software, even Excel, will give us the p-value. So we are able to reject or accept and so on. But we have 2 ways to do this. One, we can use the p-value that we calculate using a software and the level of significance to decide if we accept the null hypothesis or not. The second one is that we can compare the statistic. This one will guide us. We can compare the statistics and the critical value. And do you remember where we were getting our critical value? From the Z and T table. So there are 2 ways. If your level of significance is 5, you can use the p-value that the software will calculate for you. You just compare and make a decision. Another way, the longest route, is to go and try to calculate using the tables, which of course can consume a lot of time and so on. But we are going to see both the 2 ways. So we have a table here. So this is what you call the test statistic, this part. So we have populations, population variance, samples, statistic that you are going to use the variance. This is the test statistic. So basically here, if you are going to use the manual way, you calculate the test statistic, then you compare the test statistic with your critical value that we read from the table. So the decision rule, we are saying that there are several ways to phrase the decision rule, and they all have the same meaning. You reject the null hypothesis if the test statistic that we calculate using these formulas that you see here, these formulas are the same ones that we had almost yesterday. Because the first one, this is the test statistic when the population variance is 1, known. The statistics is the Z table. The Z table will assist us in calculating the critical value. Then the formula for test statistics, we use capital Z, is equals to the sample mean minus population mean divided by the, this was the standard error, right? SE. This one, the sigma divided by this one, it was the standard error, right? So the decision, if the test statistic is greater than the critical value, you reject the null hypothesis, right? Another one, if the absolute value of the test statistic is bigger than the absolute critical value, you reject the null hypothesis. Like if the absolute value of the test statistic, if you calculate and find that this value that you get here, wherever I'm highlighting here, is bigger than the absolute critical value, the absolute critical value, before we read from the Z table, that's the absolute critical value, you reject the null hypothesis. Another one, if the p-value, this one is the most commonly used and easy to use. If the p-value is less than some significance level, most often, which is 0.05, if the p-value is less than the significance level, you reject the null hypothesis. So that's why we are saying that usually you'll be using the p-value to make a decision. That's the easiest one. It doesn't stress you so much. So I don't know how the theory has been. Have you understood? We are going to start the practicals. So we are going to use both the methods, the manual, number 1 and 3 mostly. 1 and 3. Those are the ones that we are going to use. So that takes us to dataset S.8.14.4. Open dataset S.8.14.4. Yes? Yes. Like? Slide 5, slide 5, okay. Sorry. Yeah. This one. Yeah. Where? The rational. If the observed statistics is too far away from 0, depending on the significant level, we reject the null, otherwise we accept it. Basically, I have explained also the same concept whereby we say that if you get a 0.00, like, it means that your null is working better. So the rationale is that like if the observed statistics is too far away from 0, depending on the significance level, we reject the null hypothesis. If the observed statistics is too far away from 0. Like basically, because the observed statistic is here, let me take you this one. Like this is the observed statistics. So the observed statistics is the same as the test statistics. So if it is greater than, for instance, the critical value, you reject the null hypothesis. So it means that if it is too away, because if it is too away from 0, it becomes larger. Are you getting it? Too away from 0, like as it becomes larger, it means that it will automatically go beyond the critical value. And we see that if it becomes more than the critical value, you reject the null hypothesis. Because when you are doing your study, your objective or your prayer is that you reject the null hypothesis. Because if you don't reject it, it means your study has failed. I don't know if you are getting the concept. Yeah.
Now I was wondering
Yeah.
if you do it just with the four digital, 4 decimal points.
Yes.
That's with the larger.
No, it's not based on the decimal points. Like perhaps you can get a value for you to, for instance, for you, we have two aspects here: the test statistic, which you get from the observed, and we have the critical value, which you read from the table, right? So your prayer is that the critical value should always be small, then the test statistics higher, so that you are able to reject the null hypothesis. So what you are saying is that, yeah, it can be based on the decimal points, but it is not always a decimal point. You can even get a value of 1, 1.5, a bigger value. So away from 0, it means that it increases. Like if you count 0, 0.1, 0.2, you see it keeps on increasing. When you reach 0.9, you go to 1, 1.0, 1.1, something like that. That's the logic they are trying to say here.
If it passes 0.05, you accept.
If it passes 0.05, yeah, you accept the null. You accept the null hypothesis. Also, to accept the null hypothesis is the same as rejecting 2. It is the same as failing to reject it. If you accept the null hypothesis, is the same as failing to reject the null hypothesis. Meaning, in such case now, your status quo will remain the same. Like whatever you are trying to innovate will remain the way it was. Something like that. That is what it means. Okay. Any other question before we look at now the practicals? Okay, open dataset S.14.4. Just a minute. S.8.14.14. So, okay, I don't know if you have this one. You are supposed to have this one. I don't know if it is there. Like, the status quo here was that the average salary of a data scientist based on the Glassdoor data was 113 USD. In case I deleted this one, just input it. So we are trying to test that, to say that the average salary of a data scientist is not equal to 113, right? So I want us to, I don't know, go to insert, come here where we have the text here, text. I want us to insert our text here so that we are able to our null hypothesis. Our null hypothesis, which is represented by H naught or H0, is that our null hypothesis is that the salary, just say salary because of space, is equals to USD 113.00, right? So our alternative hypothesis, which is H1, is equals to salary is not equal to 113. So this, yes, the textbook. You come here, insert, then it is somewhere here. Then when you click this arrow, you can get textbooks, the first one. Yes? Okay, let me check. So we want to test if the salary is, if they are going to maintain a status quo or not. So, to test this, first, based on our data, the test for the mean, whereby the population variance is known, right? And our sample size is 30. Are we together? Because we are going to use two methods. Okay. Basically here we don't have the confidence. We are testing at 95% confidence interval. At 95% confidence interval. So the first one, let us go back to our notes. So population is 1. Population variance known. It means you are going to use the Z. So the formula for the test statistic, which is the capital Z, is the sample mean minus the population mean divided by the standard error. Are we getting? So let us go back here. Sample mean is equals to average of our data set sample size is equals to 30. Standard error is equals to standard deviation, population standard deviation given, right? Divided by the square root of SQRT of the sample size. So so sample mean population standard deviation. So you want to see if the average, if a data scientist in as per the Glassdoor data, not the average, like you want to know these ones if they earn 113 or no, not 100. Like the average salary of a data scientist as per the Glassdoor data, the salary of a data scientist as per the Glassdoor data is equals to 113, and we want to see, we want to justify, we are saying that it is not equal to. So in this case, we can define further by saying that the population, like our null hypothesis, becomes H naught, the population variance, so the population mean is equals to 0 or is not equal to 0, because we have not been given, we have not been given the population mean. So like this hypothesis can further be defined by saying H naught mu, I don't know, there's a symbol for mu, but for now I allow you to use u, is equals to 0, while H1 sorry, shift H1 mu for the population mean is not equal to 0. So but I'll show you the other method is the easiest. You don't have to have all these hassles. So now let us calculate the z-score. The z-score, we have two z-scores that we are going to calculate. We have this one, the capital here, whereby we are going to minus the sample mean minus the population, assumed population mean divided by the standard error. Then now we are going to calculate the small z from our z table at 95% confidence level. So let us come back here. Let us start with the z-score, the statistic, the capital one. So that one is equals to the sample mean minus 0 divided by the standard error. But ensure the upper side you have put in bracket. Is it okay? I think that is what. Sorry, there's something wrong. It is, where is the notes? X minus mu, sigma divided by the square root of 9 is the sample, is the standard error, right? Which we have it. Sample mean, why am I getting a different value from what I had done? Sample mean minus, sorry, J5. Sorry. I understand what the mistake. The mistake here, these people had given us the population average salary. This one. So this is just the formulation of the hypothesis, but this one they had given us the population. So instead of 0, we are going to use the 113. This value is what they had given us. Are we getting it? That's why I was wondering where I was getting. But this is just how it can, the hypothesis, how it can be formulated mathematically. A point of correction. So basically here, we have the sample mean and they have given us the population mean. So we are going to subtract this one, that one. So that's the z-score. But in statistics, mostly we work with the absolute values. Absolute values here mean the positive values. Like we work with the absolute values. We have the negative one, but we are going to read it on a positive side, absolute values. The next one, according to our notes, we are saying that the test statistic should be greater than the critical value. We have the, yes? This one here, it is the sample mean minus the population mean that you have been given divided by the standard error. Yeah. It is almost like standardization, but the only difference when you are standardizing, you are dividing by the sigma alone. But now up again on standardization, it was x, not x bar, right? If you can try to relate the two. So that is it. The next thing, according to our notes, we have the test statistics. We need now to look for the critical value. Are we together? The critical value. So critical value at 95% confidence interval, and it is a two-sided. We are going to our table to look for 0.025, right? So our Z table, where is it? Let me look for the Z table. It was on inferential statistics. 0.025. Okay, it was now is equals to 1 minus 0.025. Then we go to look for 0.975. It was on 9 something. Yeah, 1.96. So that is 1.96. Where is it? Which is here 1.96. So we have our critical value, we have our test statistics, but for this one I said that we are going to work with the absolute value, which is 4.67. You don't consider the negative, you work with absolute value in statistics. So going back to our decision, we are saying that we reject the null hypothesis if the test statistics is greater than the critical value. So let us go back. Test statistic greater than the critical value. So what is our, coming back here, what is our test statistic? Our test statistic value, it is equals to 4.67. What is our critical value? Value is equals to 1.96. So we are saying that reject null if test is greater than, or what is it saying? Test is greater than critical value. If test greater than critical value. So according to our data, test statistic So according to our data, we are going to reject the null hypothesis, right? Because reject if test is greater than critical value. But in our case, our test statistic is 4.67, which is truly, it is greater than our critical value, which is 1.96. So we can say that. How are we going to report it? There's a, we had somewhere, so we are going to say that at was our significance, 5%. So we are going to say, we are going to conclude by saying that at 5% significance level, we reject the null hypothesis. And for what's the conclusion? Is that the average salary of a data scientist in Glassdoor is not equal to 113 USD, right? So we conclude that at 5% significance level, we reject the null hypothesis. Therefore, we conclude that the average salary of a data scientist Glassdoor, or according to Glassdoor data, is not equal to that value now is not equal to 113 USD. So that is one way of testing using the critical value. And then, so there's another way whereby we look at the p-value and our significance level, which is 5%, right? I don't know if this will work. Let me try using the data analysis tool for the weakness about this one, it doesn't have t-test paired, it doesn't have for one sample. But let me check on the descriptive statistic and see if it's going to work. It will give us labels, confidence level for mean is 95%. If it is 5, then new worksheet. Let me see. Why is it? Okay, there's something I haven't selected. Let me try. I'm trying to see if it's going to give us the p-value on descriptive. On this one, I'm not very sure. And what have I for summary statistics, right? Does it give us the significance, the mean, standard error, median, mode, deviation, variance, kurtosis, skewness, range? No, it doesn't give us the small value that I wanted. Okay, this one, you have to go the longest route. When we go and look at the two populations, we can use the shortest route the way we did yesterday. Yeah. So we have tested for the mean population variance, known. Let us test if the population variance is unknown. This is known. Let us look at, so that is, let us test for that, then you go for a short break. So before that, there's an exercise. The exercise on whatever we have done is S.9, S.9.14.4. 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 So the next data set I want you to open is S.12.14.6. 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 S. S.1214. Oh, yeah, sure. Okay. Thank you for that. S.1214. Test for 1416. It is test for the mean population variance unknown. So this one is interesting. It is S 121416. So this one is interesting. So you have the open rate data set, then the more data. So perhaps in this one, for this one, you are working as a marketing insights data analyst in your company. In companies, we do have various marketing methods, right? So you run a campaign, a Facebook campaign, whereby the customers were directed to this. It's not a Facebook campaign, so you run an email marketing campaign. You see the blast email, they are called blast, like you send to various people. Like if you have an event, we do send a blast email. It addresses your specific batch. It picks from the entire database. They are called blast emails. So when you send a blast email, the systems are able to show you the open rate, how many people opened, how many clicked, and also how many subscribe or unsubscribe, and how many have you sent to that person, right? So we have the data set here, as you can see. So your manager has told you that your open rate for your email has never been more than 40%. Like, that means it's less than or equal to 40%. The average open rate of your emails has been less than or equal to 40%. Therefore, he has informed you, as an analyst, you are trying to tell him, no, let us test to know if this is true or not, because for him, he has just mentioned it. So it means that you need to formulate a hypothesis. The alternative now will mean that the average open rate is greater than 40%. That is what you want to test, to justify if truly whatever the status, you are trying to challenge the status quo of your boss, because that is your role, to justify using data for him he has just mentioned. So that one takes us to This is the more data. So we have the data set here. I have summarized it because I was interested in this column alone, right? This is the column we want. Open rate. So here we want to test for the mean. The population variance is unknown. The data set is population is 1, right? Then what do we need? Based on this, which type of a test is this? Is it a two-tailed or one-tailed? Two-tailed. Let us go back to the notes here. Here. Where is it? Two-tailed and one. We said whenever you see less than, greater than, equal to, it is a one-tailed. So we want to test at 95% significance level. Where is it? I want us just to test at 95, leave alone the 5, this one. I just want us to test at 95% alone. Significance level. If you are going to reject the null hypothesis or to fail to reject. So, the first thing, let us formulate our hypothesis, right? Let us insert our text box. Insert text box. So, H note, the null hypothesis is equals to that open rate is less than or equal to 40%. Less than equal to 40%. The alternative hypothesis that you are trying to challenge is that open rate alternative is now is greater than, right? Like you are trying to say that the average open rate is more than 40%. Okay? So this one is a one. You can note further that one-sided test. So let us start. The statistic that we are going to use according to our notes here, because the population is 1, the population variance is unknown. The statistic that we are going to use is the T, or the student's T statistic. So let us go back to our data set. What do we need? We need to calculate the sample mean, right? Is equals to the average of the open rate. We have 37.7. The sample standard deviation is STD EV dot S of our open rate. Okay. The standard error is the standard deviation divided by the square root of a sample size. So let us find our sample size. Sample size, it is what? You can count. Our sample size is count of this. It is 10. So our standard error is the standard deviation divided by the square root of the sample size. You are getting 4.34%. Yes, are we together? So the null hypothesis value is 40%, right? Yeah, it is 40%, the average open rate. So what do we lack? What are we lacking? Let us calculate the test statistic first, the T, right? Which is the sample mean minus the population mean divided by the standard error, right? S divided by the square root of n is the standard error. So our t is equals to the sample. You have said it is the, sorry, it is the sample mean, which is that 7 point something, minus the null hypothesis value, which we have been given, which is the average population mean, divided by the standard error. Yeah. That is what I had gotten when I was preparing. Yeah. So we are done with that. Of course, we will take the positive value later. So, given that this is, we are testing this at 95% confidence level. So our significance value is 5%. And given that it is a one-sided test, we are not going to divide the 1% by 2. And another thing, it is a t-statistics. Our degrees of freedom is n minus 1. So 10 minus 1, it is 9. So now we are going to our t-table. Where is our student's t-table? Inferential statistic. So we are going to read at 9 and 0.5% is 0.05. 9 and 0. This one is 1.833. 1.833. Where is it? It is 1.833. So leave alone the two-sided, we don't need it. We don't need it because we are doing a one-sided test. So, yes? No, we are not doing a half. We say that our alpha is 5%, right? And when we are reading from the T table, given that it is a one-sided test, we are not going to divide it by 2. We are going to carry the way it is. Are you getting it? You remember initially we used to divide by 2 because it was a two-sided test. It was equal to or not equal to. But here it is a one-sided test. Yes, both of them were still at 95% confidence level, but now when you read from the table, if it is a two-sided test, you divide by 2 your alpha, right? If it is a one-sided test, you carry the entire of it. That's why we have carried the entire 5%, which is 0.05. We haven't divided so that it becomes 0.025. Are we together?
But you see that this 1.833
Yeah.
is at 0.05.
Yes.
Why have you not taken the value in 0.025?
Because it is a one-sided test. Are you getting it? Let me take you back to the notes. It is here. Where is it? Where is it? It is here. let us go back to the notes. We are saying that it was level of significance and type of test. We say that level of significance is the probability of rejecting a null hypothesis that is true. And we have the three main ones here, right? 0.1, 0.05, and 0.01. Which of course we express as percentage. These are 10%, 5%, and 1%, right? So we have two types of tests, two-sided, or what called the two-tailed test, and the one-sided or the one-tailed test. The one-sided test is used when the null does not contain equality or inequality sign. So it is used when you have the less than sign, the greater than sign, the less than sign, and the greater than or equal to sign. And the rejection reason is based on the alpha as a whole. Do you see here? But when we come the two-sided test, used when the null hypothesis contains equal to or not equal to. And rejection region is based on alpha divided by 2. So if it is 5, you divide by 2, it becomes 0.025. So that is why, like going back here, so this one in mathematics means is less than or equal to. Like, it's like if I remove this one and bring the hyphen like down here, I don't know how I can do it. It is not possible. That's why instead of writing like that, even if you write like this, still it means it is not equal to in mathematics. Not equal to, like it's less than equal to. Like instead of using the V and the symbol, it means the same thing, not equal to. Or perhaps let me open my whiteboard. I demonstrate that quickly. Okay, let me open my whiteboard. So if I write this one, for instance, it's the same as to say this one. This one means the same thing with this. The same, less than, equal to, is the same by saying less than, equal to. They mean the same. Which is total difference from equal to and not equal to. These are totally different from these ones. So, going back to our example, it was less than, equal to, and greater than. So it is a one-sided test. Therefore, when you are going to read the value, the critical value, you don't divide the alpha by 2. You take the whole of it. Justus, is it now clear? Okay. So where were we now? To make the decision. Do we have everything? Yes? Already we have our critical value. We have our t-score. Of course, we are going to take the absolute value, which is 0.53. So now it's decision. We need to make decision. Decision. Let me pick someone. Elvis, are you in a position to speak? Elvis? Elvis? Okay, let me just explain because of time. So, what's the conclusion? We say that we compare what with what? Going back to we reject the null hypothesis if the test statistics is greater than the critical value. So in this case, our test statistic is 0.5 3, right? And our critical is 1.8. So in this case, our test statistics is less than 1.833. So in this case, we are going to reject or fail to reject. So if we fail to accept, to reject, it means we are going to, okay, yeah, we accept the null hypothesis. So it means the manager was right. So the conclusion we can make is that we can conclude by saying, okay, we say we accept the null hypothesis at 5% significance level, right? Right? So we conclude that the email marketing open rate is less than or equal to 40%. So it means the manager was right. Right? Yeah. So it means the manager was right. Like his claim was, like whatever you are trying to disapprove as the marketing insights analyst was, like you are trying to confirm truly or if what he's saying is okay or not. So we accept the null hypothesis at 5% significance level. We conclude that the email marketing open rate is less than or equal to 40%. So that takes us to assignment. S.13 S.13.24.6. The assignment is S.13.24.6. S.13.24.6. So I like to give you a short break. I don't know if you have the energy. We are remaining with 3 concepts only. Let us assess, then we close this unit so that you don't come tomorrow and Friday. We meet on Monday for revision. Is that okay? Or you want to come tomorrow? Yeah. So only 3 concepts remaining. So just go for a break up to 15 minutes from now. It will be around 11:50. Yeah, then we come back and proceed.